FTP, and it is based on the final day and final session. Title of the session is Microgrid Design and its Feasibility Studies using Homer. And today's resource person is Dr. Rohapati Venkatesh. Okay, only 2 lines. Sir has done his BTech in Electrical and Electronics Engineering in Acharya Nagarjuna University and MTech Power Electronics in BMS College of Engineering, PhD on Renewable Energy and Microgrids from NIT Trichy, and currently he is working as Associate Professor in BMS College. Welcome to the session, sir. And I invite Dr. Prem Master and sir.
I think everybody knows that microgrid design and its feasibility studies. You have some idea about microgrids. Right? Everybody are working on microgrids and design, but this topic is something different from whatever you are doing research. Anyone knows Homer here? Homer software. Anyone working on Homer? Any papers on that?
Quite sometimes I work with the Homer Grid and also Homer Pro for quite some time, but not thoroughly.
What was your input and the outcome of the feedback about that?
So as far as this, specifically this microgrid studies are concerned, there are certain options which they have given, which we can directly, we can capitalize on it. Like fuel cell option is there, solar PV, and all those inbuilt options are there. So accordingly, we can give some inputs based on our design, whatever we want to pursue. So based on that, it will give some certain outputs. That is what we have.
See, generally when we wanted to design some microgrid for any kind of application, suppose Dayananda SAGAR college we wanted to design, or some BMS college we wanted to design, some particular community load we have. For that particular load we wanted to design microgrid means we need to study, feasibility studies is important. That feasibility studies can be done by using Homer software. Suppose I want to install 1000 megawatt of solar PV power plant. What I have to do? For that particular location, whether the solar PV system is feasible or not, for that particular latitude and longitude, what is the outcome I am going to get? What is the yields I am going to get? If I install, what is the payback period of that particular power plant I want to know? Suppose when you wanted to analyze only solar PV systems, you can think about PV-Syst kind of software. But when you talk about PV-Syst software, it is not possible to integrate hybrid energy sources. Different energy sources it is not possible. Sir was telling fuel cell it is possible to integrate, wind turbine it is possible to integrate when you talk about Homer. Like that. That means when you want to design any solar PV power plants or hybrid energy based microgrids, first we need to conduct feasibility studies. That feasibility studies in terms of economical operation also we have to conduct, in terms of optimal sizing, simulation point of view also we have to conduct. Suppose this is the area of the room. In this area we wanted to develop one solar PV system. What is that basically we are going to do? How much yields we will get per annum? First we need to analyze. And when you install, how long it will take to payback period, how much it will take. All those things analysis can be done by using PV-Syst and Homer. What is the disadvantage in PV-Syst is we can't able to integrate multiple energy sources. Suppose wind turbine is not available there. Only solar is available there. Diesel generator it is not possible to integrate. Now we'll just see. This is the outline of my presentation. First one is, when we wanted to study feasibility studies of a microgrid, first we need to understand what is meant by microgrid. Some introduction we will discuss about microgrid and components required for designing of a microgrid, and what are the advantages of microgrid design and challenges in microgrid, what are the problems we are facing and how to address that problems. We will discuss classification of microgrids, and basically we are going to concentrate more on homework used for feasibility studies, in particularly designing of a microgrid applications. I am going to discuss one case study and I am going to discuss different configurations. Suppose you have solar, PV, biomass, what is the LCOE, net present cost, and what is the contribution from solar PV system, and what is the contribution from wind system, how we are optimizing, how we are sensitive, how we are doing sensitive analysis, all those things we are going to discuss. We all know that what is even microgrid. A microgrid is a small power system. It can be connected to the grid, or we can operate in a islanding mode of operation also. That means autonomous microgrid and grid connected system. Microgrid may be small, power only few buildings. We can only power DAYANANDA College or some community, whatever available. Large power, okay. Many microgrids today are formed around existing government. That means sometimes we may have to, our application may be heat and our application may be power supply also. During that particular instant, we may have to produce heat and power, both the things. That kind of microgrids also available. Nowadays, all these microgrids are designed or powered by using solar, wind and small hydro systems. What are the key components of microgrid? When we talk about microgrid, the microgrid consisting of 5 key components. The first one is energy sources, that means generators are required, or energy storage system is required, batteries is required. The next one is energy sinks, that means loads are required, loads must be there in the microgrid. And disconnecting and connecting system, the means of connecting, disconnecting large power system. Sometimes when we have excess power, we can operate connecting to the grid, or we can operate isolate, autonomous mode of operation also. Controlling, then regulating, controlling also comes into picture. And safety measures, protection is also one of the components when we talk about microgrid. Now, what are the advantages of microgrid? Why we need of going to the microgrids? When we integrate your microgrid to a grid, or when you run the system autonomously, what will happen in a microgrid when you adopt this kind of technology? It improves the reliability, reduce the energy cost. You can optimize the system better than the previous existing system when you integrate this. And you know that when we talk about microgrids, we are going to integrate many renewable sources. All those sources are comes under clean energy, increase sustainability, and next one is security can be increased, and improve grid operation. Microgrid can improve the operating stability of the grid. How it is improved? Operating stability of the grid by using the microgrid with the help of what is that? How can we say this is one of the advantages? When we integrate whatever the microgrid we design with the grid, how do we say the stability of the grid is increased?
We can optimize the resource allocation.
We can optimize the resource allocation, and we can operate the, when we talk about economical point of view also, one of the better kind of economic development. Microgrid can provide, now many places we don't have electrical power supply. That places we can give power supply from this microgrid by designing this. Now, what are the challenges we are facing when we talk about microgrid? The major challenges what we are facing when we talk about microgrid is technical, economical, and market and regulatory bodies. Regulatory bodies means administrative issues, policies, and all will come into picture. When we talk about technical, energy management, operational issues. Energy management in a microgrid is one of the important thing, and design, security, power quality is very important in microgrid, and stability, load balance is the one of the important thing, and components and compatibility. See, in these components and compatibility, equipment specification, that means many people are working on optimal sizing of a DGs. That means sizing of the DCC is one of the area. That means equipment specifications, feeder design, communication and protocols is also one of the important things. Integration of distributed energy sources. That means when you integrate distributed energy sources, so many power electronic systems comes into picture. You need to integrate to the grid, or sometimes you may have to take the power supply from the grid. Protection is also one of the challenging tasks in a microgrid. Economical point of view, when we talk about ensuring the cost effectiveness, increased power cost, high cost of remote microgrid, high cost of DERs. Now in this presentation, with the help of Homer, we are going to concentrate more on economical aspects. That means when we wanted to design the microgrid, what all to be considered and what is the cost of each and everything we are going to consider. We are going to see. Now what is that, how these microgrids are classified? These microgrids are classified based on different aspects. One is control point of view, another one is size point of view, power supply point of view, source point of view, scenario point of view, location point of view, application point of view. When you look at the control point of view, it may be centralized or it may be decentralized microgrid. But when you talk about size, we all know medium, small and large size microgrids based on the capacity, we can say. Power supply point of view, AC, maybe AC loads are available, maybe DC loads are available, maybe some microgrid consisting of AC loads, both DC loads. Sources point of view, some microgrids may be working only on renewable basis, some microgrids are working on fossil fuels, some are combined with renewable and fossil fuels. When it comes to renewable is again classified into solar, wind, biomass and hydro and hybrid. Then scenario point of view, that means load point of view, residential, there are different loads, residential loads, industrial loads, commercial loads, etc. Location point of view, we can design for a urban load applications, we can design for a remote load applications. When it comes to applications, suppose for your own home also you can design for nanomicrogrid nowadays. That means what we can say for campus applications, for community applications, for islanding, for district energy applications, all these things can be designed. With this, I am going to take one small microgrid. That microgrid is designed with the help of Homer. Okay.
Homer is open source software.
No, sir. It is 21 days trial version.
Trial version.
After that, you have to pay. This is the introduction to Homer. Homer micro optimization model. This is a computer model. Actually, this is developed by NREL, National Renewable Energy Laboratory, US. The objective of this Homer software is to design hybrid energy based microgrids and micropower systems. That means, as I told you at the initial stage, you wanted to develop one microgrid for your gated community. First, what we have to do, we need to do feasibility studies. How to do feasibility studies? Whether it is feasible for that particular location or not. Is it possible to just analyze without any software? It is not possible to just analyze and tell that this is the yields we will get for this particular location, for this much biomass I will get, this much solar I will get, this much wind I will get. How Homer analyzes this and gives us results, and that results are almost 95% equal to, that means 90% equal to, 95% equal to the exact results, exact performance what we get when you install really. There are many articles on that. Whatever they simulate, whatever they get results, that results are almost, whatever the performance they do in terms of simulations, that performance is exactly almost maybe 3 to 4% variation will be there, matches with the exact performance of the system. Suppose I wanted to design a microgrid for a DAYANANDA college. From where to start? What I have to do first? First, I should understand the load characteristics of this DAYANANDA College of Engineering. That means, what is the load variation for 24 hours? What is the load variation for quarterly, yearly, 6 months? What is the load variation? To meet that load demand, I wanted to select what are the sources available. The resources available in the NSRI is different. The resources available in some gated community is different. The resources available in some apartment is different. That means now I wanted to conduct feasibility studies. I want to know whether my project will give good results or whether I am able to implement for this particular location. Generally, you may wanted to install solar. You may wanted to install wind for this particular location. Or you are estimating what is the biomass output of this campus. Suppose per day this many tons are coming, per week this many tons are coming. Now you want to add that also. When you add that one also, what is the feasibility of this? How many units I can generate? How much can be contributed from biomass? How much can be contributed from wind, solar, fuel cell, etc. That can be done. That means initial stage studies can be done by using this software. Homer models a power system physically, behavior and life cycle cost. That means what is the life cycle cost? How to fix the unit cost. Suppose we are generating some units. What is the cost of each and every unit when we generate power from that particular microgrid? That can also be assessed by using this Homer software. Homer allows the moderator to compare many different designs. Sometimes what will happen, we need to select optimal design. Wind may not be a feasible solution for this particular location. Maybe solar and biomass is feasible solution for this particular location. Then what we have to do? What is the analysis, what is the assessments we do when solar and biomass is active and DG is active? What assessments we have to do when solar, biomass and wind is active? And what is the contribution from that? Okay. When you wanted to understand this, first of all, for this particular location, you should know about irradiation, you should know about temperature, you should know about wind speed, wind velocity, all these things, correct? Correct? Practically, we will not have all these things when you wanted to analyze. How do we integrate that to your Homer software? Homer is having an option of taking the data from NASA meteorological data. That means if you are giving latitude and longitude of this particular row, you can extract what is the irradiation, what is the temperature, what is the wind velocity of this particular latitude and longitude. There is a NASA meteorological data you can extract based on this latitude and longitude, and whatever you are simulating, whatever you are designing, that is the input of your analysis. That data NASA meteorological people are maintaining from past many years. They will be updating. That means almost some 15 years, 16 years data will be there. Based on that, it is going to analyze and you are going to get a results. Homer basically performs 3-level simulations. One is simulation, optimization and sensitivity analysis. That means uncertainty analysis. Simulation means you are just going to take, as I told you in the previous slide, you are going to analyze your load characteristics. You are going to analyze the resources available in your particular system. Based on that, you are going to simulate. Then after that, optimization comes into picture. Which configuration is more optimum? As I told you, there are different types of DGs you have. Which one is more optimum to run in that particular instant? That is also analyzed with the help of optimization. Then after that, uncertainty means, suppose when you are considering example, diesel generator is considered one of the DG in your microgrid. When you consider that, uncertainty means the fuel cost is not constant there. The fuel cost is varying with respect to year or with respect to time. When it is varying, how your optimization, what is the cost changes, LCOE changes. Similarly, you can talk about any uncertainty issues. Any uncertainties can be given while simulating. Based on that, each uncertainty thing you are going to simulate and you are going to get a results. And your analysis will start there. in this presentation, just introduction to microgrid over and what is the importance of Homer and how what and all we can do in Homer. That's what we understood. Now we are going to look at one simple case study. The objective of this case study is novel model for autonomous microgrid. I am not going to connect this microgrid for a grid integrated mode. Autonomous mode of operation is going to happen. To perform optimal sizing and techno-economic analysis of proposed system. Whatever the proposed system is there, optimum sizing we are going to do, and one more thing is techno-economical analysis we are going to do. And as I told you, different configurations we are going to discuss. Different configurations means which configuration is better. When you operate in this configuration, what is the outcome of that configuration? Next configuration, what is the outcome? How to select? How to go ahead, we are going to discuss. This is a simple autonomous microgrid I am just considering for the simulation purpose. This is simple block diagram. I have solar PV, diesel generator, biomass source, electric load and wind generator. First, as I discussed in the previous slide, first I analyze the electric load. What is the load demand? Based on that load demand, I started selecting my DGs based on the resources available. Okay. Now, when you look at, see, when you enter into Homer software, you have different types of DGs there. This is the representation of the Homer symbols. You have primary load, you have biomass, you have wind. There are other sources also. I have not taken that. As he told, fuel cell is also there. I have not considered for my simulation. Fuel cell is not considered. I considered only biomass, wind, solar and DG. Okay, as we discussed in the previous block diagram. The same thing is simulated in a Homer. When we simulate in Homer, here when we look at this, you have A, B, C, D, E, F. There are many options. These options is called configurations. See, when you look at the figure A, you have wind, biomass, and there is a battery storage, and there is a solar PV, and there is a bidirectional converter. And when you look at the figure B, something is not there. Wind is not there. Now, same thing if you assume that for your load application, this particular system is designed for DAYANANDA load application. For this particular system is designed, you are going to analyze when all the sources are active. That means PV, battery, wind and bio is active. What is going to happen? What is the contribution from PV? What is the contribution from wind? What is the contribution from biomass? How many hours of biomass? How many tons of biomass is required? How many units we are going to generate from PV? How many units we are going to generate from wind? Because for this particular schematic, the input what we have given already from the NASA meteorological data. The irradiation, velocity and temperature is already given. That means whatever the solar PV system you are selecting, the performance output is almost based on this latitude and longitude of the system. Now when you look at figure B, wind is not there. The second option is wind we don't have. What is going to happen? We'll see in the comparison table. Next when we look at the C, PV is not there, only biomass is running. Biomass generator is continuously running to supply the load demand. When we look at the figure D, biomass is there, wind is also there and battery storage. There is no solar PV. Like this, you are going to get different configurations and different options of design. By looking at these results, this is the options, we will see the results later. You will get to know which one is more optimal. When you wanted to design any kind of microgrid, what all the parameters you are going to consider? What are the parameters you are going to consider? Economical point of view. Net present cost should be less. LCOI should be, unit per cost should be less. That is the one important thing. And one more objective what you will keep, more energy generation must be there from renewable, because we have diesel source also here. Diesel generator is also there. Correct? 100% contribution we may think about renewable energy sources. That is the objective we will keep. Is it clear? Now, first, before going to that, this is actually the mathematical modeling. How Homer will respond, the background of Homer. That means each solar PV is working. What is there behind that? How solar PV system is responding, how solar PV system is producing yields, how can we calculate performance ratio, how can we calculate capacity utilization factor. All those things can be done by using mathematical modeling of a systems. That means Homer consisting of a mathematical models, each and every component you are taking, all those models are mathematically modeled. See, the first one represent solar PV model and second equation represent wind system. Here we have biomass also. I considered when we look at the our block diagram, we have biomass also. The biomass is also modeled using this. Similarly, this is the biomass and this is the economical operation of the system. What is meant by LCOE? Here, when we talk about this Homer, LCOE and net present cost is very important. LCOE and net present cost is important. What is meant by LCOE? Why we need of giving more importance for LCOE when we design any kind of power system, power generating station or microgrid, anything. What is the importance of microgrid? LCOE means sum of entire cost collected during the project lifespan to the kilowatt generated, how much generated from that power plant over the entire lifetime of the project. This is what we are going to assess from this. Then one more parameter what we are going to do is, we are going to analyze the net present cost also. What is it by net present cost? When we talk about economical operation of the power system, there these parameters comes into picture. Net present cost is also important. Total cost of the system throughout the project lifetime minus the present value of the total revenue generated during the project lifetime. That means how much in revenue we generated. Now, as we discussed, modeling of proposed system architecture using Homer. How to model it? See, as we discussed in the previous slides, first we are going to understand the load profile for a particular case study. Whether it may be community, whether it may be anything, college or something. We are going to first understand the load profile. After understanding the load profile, that means what is that we are going to do when we are simulating? We are going to give load details. 0 to 1 hour, what is the load? 1 to 2 hours, what is the load? If any variation is there from 0 to 1 hour, also we have to give. It will not be constant, correct, for 1 hour, it may be varying. That means load curve we have to prepare first, whether it is daily load curve or whatever it is. Then after that, resource types, we have to decide for that particular location what resources we have. Suppose I selected this simulation is done for some Denmark, some university. Okay, latitude, longitude is taken for that particular university. What next we'll see what are the resources is considered. The resources means what is the solar input here, what is the wind, what is the biomass considered, what is the suppose if you are considering fuel cell, what is the fuel cell capacity, what is the DC capacity, what is the load capacity, all these things we have to give the details. Then after that, resource availability, anyway we discussed technical specifications. When we are doing the optimal sizing of a DGs, we are going to concentrate what are the different types of DGs, how we have to connect, which bus we have to connect, all those things. Similarly, what is the size of solar PV we have to select for to meet this load demand? What is the wind we have to select to meet this load demand? All those things we are going to, technical specifications we are going to give when we enter in the software, when we wanted to simulate. Then project economics. Now you are going to fix what is the levelized cost of the energy you want to give, you want to sell. Suppose you can operate the system with grid connected mode also, you can operate the system with standalone mode also. Suppose when you are connecting same system to the grid connected mode, then you need to mention there what is the energy generated when you supply to the grid. What is the cost of the energy? Suppose 1 unit, 1 rupee, like that. When you receive from the grid, what is the cost? Is it clear? You have an option to fix that. The energy generated can be sold, correct? What is the cost when you send it to the grid? When you receive from the grid, what is the cost? Like net metering concept, what is happening in Bangalore? Then analyze all feasible solutions. Then you have multiple sources. Each and every configuration is analyzed. Then prioritize best scenario case based on the objective functions. Whatever the objective functions you are creating, based on that, which one is best? You have multiple options. We discussed some 9 figures, I think, 9 or 8. In that, which one is best? How do we decide? Based on the LCOE, what we have given is common for all the configurations. The simulation is running for all the configuration. When this system is working, what will happen? When this system is working, what will happen? When this system is working, what will happen? And there is an outcome of each and every system. Then we are going to compare all the things and decide which is the better design. And as we discussed, simulation and optimization, sometimes what will happen, you want to check. Here I have not done any sensitive analysis. What you have to do is, when you wanted to do that, you have to change some, you have to create some scenarios. Suppose I assume that some parameters are changing based on the time. When some parameters are changing based on the time, what is going to happen to your simulation output? What is going to happen for your project? How your parameters are going to change? That means some assumptions you have to do. Suppose, as I told you at the time of starting, suppose petrol or diesel, something. You have considered diesel generator here. The cost today is 50 rupees, tomorrow, next year is 60. When it increases, when it is 50, what will happen? When it is 60, what will happen? When it is 70, what will happen? Otherwise, you can change wind velocities. You can change solar. Suppose you are not using any tracking system here. Suppose you want to go for a tracking system. You want to apply for a tracking system. Then how your things will affect? All those analysis can be under everything, with the tracker, without tracker, with shading, with change of fuel cost, with change of biomass input, all this. That how many input parameters you are changing, that many times simulation will run, and you will get a simulation output for each case. Then you have to select a best case out of that.
So as far as sensitivity analysis is concerned, whether we must do the scenario generation as well as scenario reduction, both, or either one can do the thing based on our own requirement?
You can change from the load point of view also. Load also, you can say that load is fluctuating. For Jan month, the load is different. Suppose when you talk about college, the load is different in different months. Okay, when you talk about vacation, it is different. When you talk about full working time, it is different. You can, that means what will happen? Suppose January month full working, the load is maximum. Again, the simulation takes place for that particular case study. You will get one more report on that. Suppose 1 month there is no load. That is load point of view. When you talk about source point of view, suppose solar is not available. Assume that some particular day solar is not available. You have to fix there. And suppose you consider, as I told you, diesel. This year the unit cost is 1 rupee. Next year the unit cost is 150. 1 rupee 50 paisa. Next year 2 rupees. Next year 250. You give some analysis. You give some inputs there. Each input there is a report generated, and we can analyze from that report. This is the general flowchart of a algorithm. This actually works for 8760 hours. 8760 hours. Every time the basic funda is different. Basic funda is same. The generated power is equal to losses plus load demand. That is the main concept we use when whatever we discuss. Based on that only, this is the created. Every time we are going to discuss about what is the PV generation at that instant, at that time, wind, biomass, whatever the sources you are taking, that is equal to load, nothing.
The
There is
power
no-
balance should be maintained.
Power balance should be maintained. If power balance is not maintained, you should have a source storage or you should have a double load. As per the thing. As I told you, resources. What type of resources? This resources is not actual data, but this resources matches with actual data taken by latitude and longitude. Suppose this is the, I am telling you, average variation of daily solar irradiation for Jan, February, March, April, something. This is something Denmark latitude and longitude I designed, some university. When you look at this, how it is varying. If you implement same schematic practically, if you observe this, you are going to get same results. That means this is a resources selected solar irradiation, temperature for that particular location, and biomass input I consider as a constant. I assume that there is some 8 tons biomass is coming from that particular university, and we consider. But you wanted to change the biomass is different here also you can take. Based on that, your analysis will start again. Similarly, wind variation or wind, solar and temperature is taken from NASA meteorological data. You have a access, the software is having a access to the data. Okay. Now this is the simple load, random load considered, some load considered. I want to meet this load from this particular system. Now when I simulate this kind of reports I am going to generate, the first case when PV, wind, biomass are active. First case, what is happening? PV is also available and biomass is also available and wind is also available. How much amount of energy? This is the per year, kilowatt hour per year. How much amount of energy generated from solar photovoltaic system? Some 65,539 kilowatt hour generated from solar PV system. Similarly, when you talk about biomass, 1,40,824. This biomass output may be constant because we considered throughout the year it is constant. We assume that 8 ton biomass is coming from every month, every time, every day it is constant. We have not changed that. But when we talk about this PV and wind, this is the exact actual data taken from NASA and that is given to your microgrid. And based on that, your output results are coming. And the generic 10 kilowatt is a wind turbine output, wind generator output. That is almost 46,150. And when you look at this is the monthly generation, monthly electrical energy production when you talk about first configuration, when PV, wind, biomass are active. Now, when we talk about technical specifications, what is the size of the we have an algorithm already. Homer optimization algorithm is used. The Homer optimization algorithm is used to size the DGs also and find out the economical operation, economical parameters of the microgrid also. This is the this is the very important thing. Now, when we talk about this first particular case, our PV is active, wind is active, biomass is active, as we discussed in the power generation output here. And what is the size of solar PV we used? Whatever the optimized algorithm is selected. Optimum size of the system. That is, solar PV size is 60 kilowatts, wind turbine is 20 kilowatts, and biomass is 40 kilowatts, and battery size is 74 kilowatt hour. There is converter, we discussed there is a bidirectional converter when you wanted to charge your battery or when you wanted to load, that is 29.5. And each generator or each source, how many hours it is operating. Suppose when you talk about solar PV, in a year, how many hours it is producing? It may be minimal, How many hours it is producing? That is 47770. Wind turbine, how many hours? Annual hours of operation also we can see here. Minimal electrical output Capacity factor also we are going to calculate. The capacity factor for solar PV system is 12.5. It is supposed to be more, actually it is less here. Wind turbine 26.3 and biomass always it will be more, 40.2. This is the actual working of the actual waveform in particular cases. First thing represent biomass generator output, the second one represent PV power output, the third one represent wind output, wind turbine power output. When you look at this, we can see here where the power output is more. The x-axis represent, y-axis represent time and x-axis represent day. 1 to 365 days. Where it is maximum, what time it is maximum also we can analyze. Previously we have 3 sources active, but here I have only 2 sources active. One is PV, another one is bio or active. What is going to happen? Here wind is not there. The entire load we have to meet by using solar PV system and biomass system. And we assume that our biomass input is constant, our biomass input is not changing with respect to time, because we assume that 8 ton biomass is coming from the community. When we look at this, the biomass operation changes here. And what is the PV output here? Same thing as previous case. There is no change in this because solar PV is more optimum than other sources, because the generated it is same, you see here. $65,573, 27% of actual contribution, and remaining biomass generated output is how much? 73. Previously, how much generated from biomass?
40.
How much generated from biomass? Case 1?
55.
The utilization of 55.8%. But now what is the utilization?
70.
73%. That means whatever we have to get from wind that is not operated at this particular, what will happen to this case? What is the LCOI of this particular configuration? What is the NPC of this particular configuration? We will discuss in the later slides. Now solar PV size is maintained constant, biomass size is increased or reduced. Previously it was 40. Now?
50.
Now it is 50. This configuration of design, what is going to happen? How we are going to analyze and compare with other cases. And you see here, the generate biomass output is increased in this case. You can just compare the waveforms of this with the previous waveform. The utilization is more here. Most of the time the operating range is here. Similarly, here we don't have solar PV also, wind also. These are all the best possible solutions. But after looking at all these cases, we have to select one case for a design. That we will get to know once we compare all the outcomes in the last slide. This case, solar is inactive, wind is also inactive, only biomass is running. That means 100% contribution is from biomass source. That means whatever the demand is there, that entire demand is met by biomass. Now what is the size of the biomass? 50. Same thing is sufficient to maintain the load. And what is the battery storage? 21 kilowatt hour. Converter is 6.4. We don't require much conversion here. Now PV is not there. You have wind and you have biomass. PV is not available. This case number 4. You don't have solar PV. The combination is wind and biomass. When you have wind and biomass, 61.4% is contributed from the biomass generator, and wind is how much? 38.6. Then the total contribution is. Anyone observe this? There is a excess electricity in each configuration. There is an unmet load. What is in the excess electricity? I am only discussing about this. Anyway, this primary load is constant. We have fixed this load. What about this? What about this? In all the case studies, we discussed only generation of power from different DGs, the contribution. But there are in each and every case there is unmet electricity. Percentage of unmet electricity is there. Electric load. And excess power is also there. What it represents? Is it possible to design with 0 percentage? Any microgrid design? There is a limitation for that. We need to maintain that limitation. According to that, we have to design. What is the limitation for that? When you talk about unmet electricity and when you talk about excess power generation in a microgrid. Excess power can be between 5 to 10%. 5 to 10%. It is based on the configuration what you select. It is based on the reliability what you consider. All those matters. But what about unmet electricity? Somewhere in 365 days, sometime there is no electricity in a microgrid. That is called unmet electricity. What is the percentage acceptable? Here we got some 0.0321. Whether it is acceptable?
Is there any standards?
Yeah, excess electricity 5 to 10% or 1 to 5%. Okay. But what about unmet electricity load? Electric load, unmet electric load.
It was the surplus power which is.
Unmet means we are not supplying power for some time. 365 in a 365 days, 0.0321 percentage we are not supplying power. Correct? That is the meaning, correct? How much percentage it can be acceptable for a microgrid design? Excess can be acceptable up to 5 to 10%. But what about this? And also it depends upon reliability consideration when you talk about excess. But when you talk about unmet electricity load, electric load, some 1 hour, 2 hours, or the percentage is mentioned here, 0.0332 percentage of unmet. Suppose 365 days we are supplying power, only 1 day we are not supplying. How much percentage? That is in percentage. Like that, 0.0321%. I think 1 to 5% is acceptable. I think there is nothing standard. There is nowhere it is mentioned. But excess electricity can be 5 to 10%. But this it should be very minimal. But it cannot be 0. It will not happen. It will not be 0.
So to break 5 minutes, 10 minutes. Break for 5 minutes.
Okay.
Thursday. ಹೌದು ಟೆಂಪ್ರರಿ ಆಗಿ ಹೌದು ಓಕೆ ಸರ್ ಟೆಂಪ್ರರಿ ಅಂತ taking care of ICU hostels and problem is I get a call. So you have I'll take this next.
So we're ready for first year evaluation.
It is supposed to be 31st. But there is some technical issue. Hello, madam. Hello, madam. Madam, hello.
We planned it actually, but today morning the principal was mentioning in the medical side some things are increased.
Sir, there is some problem.
Some what they told. And maybe again they will be taking options from all the students. So maybe it will be delayed again, the principal was mentioning.
Technical issue, something there. I got the message.
We planned actually 8:30 session. 12:03 planned but this is some issue came to the 6:30. Again they go for council.
31st, we are supposed to have from my emails. Now all students are sent a mail saying that we don't want to report to classes. Everybody are coming because of 31st. Now without classes we have to maintain this. There won't be any classes, but still.
Because you cannot control last minute information also. This time also you take admission scheme.
Sir, I take content. It's not standard. Then we take it. Because every time 18 admissions happen, one or two they are dropping because of the great jobs. This time, last time, now present passed out, 25 passed out, 18 were joined, 14 4 left because of the jobs. Now this year, last year, 18 joined, 2 left, 16 are left. Because we see because we get projects based on this. 14 comes up to 14 and we stop. 16 comes 16%.
Okay.
18 comes 18 and we
The department how many faculty are there now?
22. 22, one is invitation to NIT Trichy. She's
I
working.
think many are at negative.
Padmavati madam, me, Netravati madam, recently Sonia she came.
When you have completed
20 months.
21. By the time my wife was there.
She was there, but I saw her.
Okay.
She was carrying.
Yeah,
I never had any tries. They are sitting in the ground floor. They are sitting in the piano grade.
okay.
COVID time, sir.
Correct.
When is it?
Almost 2019.
I joined in 2018.
Okay.
2018, 21, 2021, and after 1 year. Exact COVID.
Correct.
2 years COVID. I also last 2 years COVID. Mine everything online. My mean, open seminar is an option. Open seminar 2 is an option. Even DAYANANDA is an option.
Why was online?
DSA DAYANANDA is also an option. He joined he's a poet and somebody famous.
I saw many people there.
Because we feel Surat is
Near also.
Surat is something terrorism. Electrical is not so. They are not getting admissions. People who join from other departments, they are not Trichy, how do you feel comfortable? Electrical department is the professors are very nobody even if you see from top to bottom, all are very if you satisfy the criteria. They don't
And even more than that, even distance also varies. If you take bus
So
line,
this is both the same
distance. It's about 300 kilometers. Which is 300 kilometers, but it's work. Because my wife worked in IT before. And DAY5 itself about 12 hours journey. But this is only 6 hours journey. Take a car, maybe 4 5 hours. This is good. It's almost after my
Surat is Trichy is better and a God road.
yes.
Somehow that name is there for Surat electrical department. Trichy they got very good name.
Now he is not taking it.
Not taking at the time we used to feel very comfortable.
No, it was a HOD also, right?
When I was leaving, he was actually.
But somehow,
He works on that industrial system, regenerative braking.
because she did MTech also there. And yes, in English, she worked on the religion. It's fine because
How many years?
my family members also knows it. That's the reason.
He travels from somewhere, he was not staying in the quarters.
Yeah, he comes from Segula.
His wife is based in
And everyone was telling how you should like that. But
Application.
yeah, Padma
Application, he attended 21 years.
Oh, so now she is the next teacher.
She attended DMS. I had to refer that. But that time, I don't know if it would fit.
After he has gone to UK for a postdoc.
After UK only, he quit DMS.
Because wife project only has taken as a
They are seniors and she also worked on this.
no, my wife worked on scheduling, not on type side. Purely battery side.
Seven sem started. Eight sem started. I'm taking 7 sem. BSOC. Power electronics students competition. We left there and we initiated something. All are power electronics only.
But most of the colleges have removed PSOC.
No, sir, you made me to power systems. I am not power systems. I don't know everything.
Operational control.
Then you worked on HVDC system.
Most colleges have removed research.
Power system.
PSOC.
That is also
Particulars you are
Very
taking.
good.
PG they have given third sem. They will not come to class. Third sem.
Third system.
Third sem PG.
PG.
Then I told
As of today, I'm just thinking that
Admissions
you
are
are
there.
power system.
18. 1 or 2 they are dropping.
Yeah, madam, I told her, madam, I accepted it, madam wants to come to follow her.
I'm not telling you that particular line here because that's what it is there. I'm telling the background is not electronics. Yeah, HVDC power electronics. And what are controlling, what are
But other person, no, tomorrow I will set up
Shall we start? Yes. In this case, both wind and bio are active. That means wind is also active and bio is also active.
Sir, one doubt is that for bio, to make a constant throughout the
Yes.
year, no? Then in these scenarios, the demand will be, generation value will be varying for all the three cases.
Operating period is changing. Number of hours operated for that particular case is different. The input is there, but it is not operated for a longer time. I am showing you now this many hours only it is operated. That operating hours is changing based on optimal condition.
Some cases exceeded that. Some cases you have to show something data, no? That is 40 kilowatts. Okay, some without only biomass means the load will be 100%, no? How you should fulfill that demand?
This one.
Yeah. See, generation.
We have a demand of 2,27,000. 100% contribution. Continuously your biomass generator is operating.
But rated capacity of biomass will be less than this system.
It's not less than this one. Number of operations also we have to see, sir. How many hours of operation? See, it is operated for 8760 hours. Got it? That is sizing. The operating time is also important. How many hours it is operated? This we discussed, I think. Now, when we look at this, when wind biomass are active, the biomass output is how much? 50 kilowatt. Wind is 40 rating size. Battery size is 21 kilowatt hour. See here, previous case what is happening? 8760 hours, the system is operated. Now, how many hours it is operated?
Less.
6. Yeah. Similarly, when PV, wind and DG are active, up to now we are not discussed about DC. This is the last case. That means I started from the best case to worst case. The first case, whatever we discussed is best case. We are going to tell that is the best design. In the comparison results, we will get to know that is the best design. Now, generally in microgrid, DG operation is not suggested. Maybe you want to improve the reliability of the system, okay, acceptable. But when it comes to the economical, environmental point of view, DG operation is not suggested. We should try to design our system with more renewables.
Recently, I have used just go to the latest transaction paper. Now is emerging DG.
Emerging DC.
See the for they added something. Some papers I think that recent to the practical papers also. But
When you talk about economical point of view, the first case is different. Now the fifth case is different. When you look at the LCOA and NTC for this case, it will be more than the first case because you are using DC generator. It is costly. Costly. Maybe environmentally also it is not suggestible. Running cost is also more. Here if you see, if you wanted to maintain, here there is no biomass. We have to run the system with the help of only solar PV, wind and DC generator. And we know the characteristics of the wind. We all know the characteristics of the wind and solar PV. We cannot predict that, we cannot believe it. We cannot depend on that. That means we have to have some reliable source. That reliable source is DC. If you wanted to, obviously when you wanted to optimize this scenario, when power is produced by solar PV and wind is equal to load plus losses, DG will be in ideal position, correct? Obviously the algorithm will be work like that only. But still, if you see how much amount of energy generated from diesel generator in this case, 75,000 approximately. That means if you wanted to operate your system with only solar and wind, you need to have a DG case. You need to have a DG to maintain, to supply this particular load demand. Previously, we are nowhere we considered, whatever the cases we discussed, case 1, case 2, case 3, case 4, nowhere we considered DG. We considered only biomass or wind or solar, etc.
You have not considered battery in your system,
Battery is there.
but in none of the cases I think you have shown it.
Some cases we have shown that. Here you see state of charge. SOC of the battery, how it is set. And how many, what is the rating of the optimal rating of the also we discussed.
But you need to consider battery in all cases, no?
It is, what is happening here is when you simulate, you will select a battery. Without battery, what will happen? With battery, what will happen? With the rating of this battery, what will happen? All the case studies, each case it is different. And sizing is also different in first case, sizing is also different in second case, third case.
Battery sizing also.
Battery sizing is also different, it is not constant.
Then how can you compare if the sizes are changing? You can compare the system, the cost or whatever you are doing. Everything should be fixed and then based on your timings or amount what you are drawing, based on it.
Here solar PV is constant and wind whatever the taken is constant and the sizing is changing based on the thing. Means when you look at the economical point of view, what is the best possible configuration? Best possible size also important here. When you talk about configuration, size is also important. The size we are not going to fix.
Okay, at the end you will come up with.
We will come back with a comparative results and we will conclude with a best possible configuration.
Report is common in all the cases.
Every report is different. In one simulation, you may get 100 reports. As I told you in the previous slides, if I keep on changing, if I keep on fixing different variables, each report is different. By looking at the reports, you have to come to some conclusion. You have to analyze the lot of things there. This case we discussed. Now when PV, wind and DG are active, now we will look at the summarized results. At the time of starting, what I have done, I just considered some load, some DGs, solar PV or wind or whatever it is. I wanted to compare. What is the LCOA of first case? 0.195. dollars per kilowatt. The analysis is done in the
Objective to maximize the LCOE.
minimize the LCOE. LCOE should be less. See, somebody wanted to purchase power. Unit cost should be less, no, sir?
Yes.
That system is a more optimal system.
Yes.
Like that, all the cases, whatever we discussed, all the cases are compared. We conclude that when PV, wind, biomass without DG with some battery storage, 74 kilowatt of battery storage,
So this
and with the converter rating of
the output of each source, how we are deciding using any optimization
output of each source.
like PV rolling first case 60, wind 20, how we are getting those values?
The sizing is done by using optimization algorithm, Homer optimization algorithm. Sizing 60 is decided by the algorithm, 20 is decided by the algorithm, 40 is decided by the algorithm. But input parameters for that particular system is data integrated through NASA. The performance yields is calculated based on the input data received from the NASA methodology. Because we are giving irradiation. I showed you one graph. Irradiation we are giving, temperature we are giving, velocity we are giving, wind velocity. All those things are not decided and given. We have taken for that particular latitude and longitude. That means input is correct. Sizing is done by the optimization algorithm, Homer optimization algorithm. And also one more
Sizing
thing.
is done based on only the cost, correct? Cost of installation.
Cost of installation, that is also one of the important, and also sizing is changing. See, solar PV we kept it as a constant, but when it comes to wind, the algorithm is searching, algorithm is finding to which one. Suppose the sizing is also happening in the algorithm.
Sir, for different, let us consider wind, the sizing will be different.
Cost is the not economic.
Power variation will be changed now.
Power,
That kilowatt. It will be some 40, 20, 60.
that is sizing of the
Sizing of the DG, sizing of the wind. Okay. See then, okay, if you are going for installing that generation, wind generation, okay, what is this rating you are considering? Maximum rating only you are considering that?
Yeah, we are suppose if we say the best system is first case, we will go ahead with 40 kW.
First case.
First case.
Considering all the three cases, these three cases will be.
We are not going to consider all the three cases.
Yeah.
All these are the possibilities.
Okay, okay.
These are the possibilities I just simulated.
What I am thinking,
See, when you simulate your microgrid, you have different, you try with different options. Out of that options, you are going to extract best thing. The best thing is based on sizing, based on LCOE value, LCOE unit cost. All those things we are going to
So
consider.
for the optimization algorithm, what is our objective function?
The objective function is LCOE and NPC.
LCOE and
NPC, net present cost. And also another important thing here is, suppose there are two options here. Homer optimization you wanted to do is do it. In this simulation we have done it Homer optimization system. Suppose you want to change your objective function. You want to write your own code. There is a integration from MATLAB to Homer also. You can integrate your own algorithm from MATLAB to Homer. And you can check, instead of checking Homer optimization algorithm available in the software, you can try with your own algorithm.
So that will be user defined.
You can define how we will integrate things like that also we can do. You want to see different results, you want to improve the performance, whatever the algorithm available in this is, when we are fixing that, we wanted to optimize with Homer optimization, or we wanted to develop our own thing and integrate. Initially it was not there. I think recently from 1.5 years, there is a possibility you can integrate your own algorithm. You can dump your own algorithm and check the performance and compare with Homer optimization. Whatever we discussed in the flowchart and all, whatever the things we discussed, it is only Homer optimization algorithm related. But when you wanted to create your, as you told, you wanted to add your own objective function, but controlling is not. I want to control reactive power, I want to control converter, all those things are not there in the software. All those things are not there in the software. That is a different area. This is different.
So constraints we cannot do.
Constraints also we can. I told you that when you are talking about sensitive, I have constraints. According to this constraint, what is my expected output? You can uncertainty analysis. Actually, this is a summary. Microgrid for community load applications is designed and its feasibility studies is assessed. The proposed microgrid is powered by solar PV, wind, biomass, and different optimum configurations are presented in terms of technically and economically. The sizing of the microgrid and its economical parameters such as LCOE, that is the main objective here. LCOE, levelized cost of the energy, net present cost, operating cost of the system is elaborated. Now, if you wanted to download this 21 days trial version is available. You have to go to homerenergy.com. Homerenergy.com. You have three options: Homer Pro, Homer Grid, and Homer Front. Whatever I discussed today is Homer Pro, not Homer Grid or Homer Front.
What type is different? Is number of
Everything is different. Here the classification is done here. Homer Pro, it is an off-grid application system. Small to medium we can generate, we can use it. And when you talk about this techno-economical optimization, we can do done here. But when you see here, Homer Front, you can go for a large power system. You can go for a large. This PPT anyway I'll share. Here also MATLAB integration is there. Previously it was not there. Nowadays you can develop whatever the 6 days program is there. Right? Many people might have explained AML techniques. With the help of the AML techniques, you can write your own code and dump into this and see the performance. The same objective function or different objective functions.
What is the cost of this Pro or Grid?
Actually, that also I didn't add. For one student, 8,000 rupees. But academic license is different, I think. One of my student is accessing this.
For 1 year.
Per year. Per year. So $106 around $10. For student, it is very less cost. For academic institute, they wanted to have, they have to approach them and they will have some procedure with it. For academic institute. For one student, it is $10.
Homer Front is most advanced.
Nowadays it is coming. Yeah. Homer Pro is the initial thing. Now Homer Front is coming. Homer. See, one thing I wanted to tell after telling this, if you want to get papers, it is very easy to get papers in this.
But nowadays, you say it's fine, but other thing is, when we submit any papers to the homework, they are not at all accepted.
Only small
Because they-
applications, you can take the data. We want some irradiation.
No. It's only we are submitting only Homer kind of results. They may not accept. Try to have, suppose one microgrid is there. Study microgrid and get actual data. Actual analysis let us do. Then compare that actual analysis with this and see what is the difference. Then we will get a very good. Suppose one microgrid is already there, or solar PV, solar power plant is there. I want to simulate that in a PV system. And I want to see the data of last 3 years, 4 years data. And I can calculate performance ratio, I can calculate capacity factor, it's everything. Same thing I will simulate, suppose. Compare both the things. What is the difference? And how can we improve the performance of that particular plant? We can simulate again here.
So if you have any further queries, we can ask it, sir.
Yes, sir.
Okay, so thank you so much, sir, for this insightful session. And now I would like to request Dr. Prem Kumar, sir, to kindly hand over the memento and LOA. Open up this.
Thank you so much, sir. One quick value training, just to put the certificate.
Kiran sir.
There was a one.
Good evening, everyone. We have reached the end of the one week faculty development program on applications of AI techniques in modern power and energy systems. According to Henry Wadsworth Longfellow, great is the art of beginning, but greater is the art of ending. These 5 days have brought together intelligent minds with torrents of information, ideas, and shared wealth of experiences and knowledge. I wish to extend my sincere thanks to coordinators and organizers of this FTP for the efforts they have put into making it success. I request Dr. Prem Kumar sir, HOD of AAA department, to share a few words about FTP.
Yeah, fine. So I hope you people enjoyed this 5 days. So one or other session was, it may be giving you some kind of insights. You take that and maybe you can start your research work. So as I said, the outcome of this FDP, it should not be only within this room. So you should take it forward and should start work on some aspect. And I want at least one the publication from this FDP. So I hope you can do it. A lot of inputs are given by the expert members. Starting from the youngsters to the experienced people, they came as an expert and they have given their thoughts, right? So take it forward, and I see this outcome should come at least in another 2 months. Let's see. Otherwise, next time I will not organize this FTP. Then don't come with any request. Yes. So thank you all.
I request participants to share their feedback about FTP.
So though it's our FTP, so why we wanted to know the feedback is, all these things, 1, 2 coordinators, they brought in and we discussed, the organizing team came, we discussed, we finalized the title, then we just fixed this FTP. So suppose, no sir, this is missing or this is good. Still, if you want to give it in a comprehension way, it will be good. If you feel that way, You can share it as a feedback so that the next step will be that we will take it forward. It's not that fault finding, it's about for improvement. Yeah, fine. You can share. Maybe especially the new joins, for the people it's completely new, right? So you can also share your thoughts. What do you feel?
So I came across to know many aspects of energy and power systems, particularly with the applications of AI technologies. I was not aware of, to be speaking, I was not aware of many of the things that, especially to that session given by you, that new microcontroller. I came to learn those things. Those things that many delegates have come to give us many new knowledges. So it was a good session, and I would like that this kind of sessions may be conducted in future also.
Thank you, sir.
And I think most of the tools that can be used to carry out any research using AI ML in power systems, I think that was brought out really well. Few of them, it was not known, especially this hardware, what was demonstrated, that was a little new to me. Homer, yes, when I have worked on Homer, but the other few tips and other things which they discussed, especially with the modeling and other things, that was really good. I think can take it forward, start somewhere, as you said, maybe some topic which was dealt with here, can start off to do some research work. And that was maybe just a foundation for us to start with the next step, especially the AIML.
That's good. So this 5 days FDP will not turn your complete life. It's just a starting point. Maybe one or other session may be useful for you, so that you take it. Any others can do. No one. So it means everything is more than everything was good. As shown there. Yeah. Fine. Thank you all. Thank you.
We'll distribute the certificate now. I request Dr. Premkumar sir to and Dr. Vinity sir, please.
Yes, most of the my colleagues.
Yeah.
Senior, they are all senior colleagues.
That's fine, sir. It's better, no?
Dr. P. Usha.
Second.
Yes, supposed to be a student.
Yeah, fine, sir. That's good actually. Yeah.
Dr. Sarana.
Congratulations.
Dr. Mudinja.
Very good is not good.
Dr. Sushanshra. Dr. Vandana. Dr. Arjun Kumar Devi. Dr. Anurag Kumar Pandey.
They take selfie.
Professor Satish B.A. Dr. Priyanshu Kumar. Dr. Sudhani. Sudhita. Professor Ganesh. Dr. Sridevi. Professor Ganesh. Now the district are certificate for coordinators. So one coordinators Dr. Anubhav Mafande.
That's it.
Suman.
We can combine and do DMSA.
Yeah, we'll
Dr.
do
Roshi
that.
Sumanana. Student volunteered for monthly only, so you know.
Complete recording unit. So day 1 to day.
No recording is happening.
Yes.
Dr. Prem Kumar.
Very good. Okay, it's for MBA purposes recording. Sorry. Thank you, sir. Everyone is fine.
Okay, now Dr. Anubhav Kumar Pandey can give vote of thanks.
Yes, so as we lower the curtain for this 1 week FTP, I would like to extend my gratitude to the management principal for their encouragement to conduct this faculty development program. I'd also like to thank our head of department, Dr. Prem Kumar M, to be the guiding light and to providing constant support from initial planning till conclusion of this event. Most importantly, I am thankful to the organizing committee members for ensuring the smooth conduct of this event. And finally, I would like to thank Kiran, our student, who has single-handedly managed the online streaming of this event on YouTube, which we have attempted for the very first time. So thank you, Kiran, and thank you everyone, each one of you, for actively participating in this event. Thank you. Thank you.
Okay, so yeah, but we'll take one group photo.
Take from this mode. 200 mode or photo mode is also used. Sir,
Sir, call you will not take part.
Certificate you listed.